Welcome back to the Deep Dive. This is the place where we break down complex research so you get the knowledge you need without having to read through, hundreds of pages of dense technical reports. Today, we are going deep. I mean, literally deep into the Earth's crust. We're exploring how artificial intelligence is giving us this massive upgrade in how we understand and classify seismic events. And when we say events, we're talking about everything, from huge catastrophic earthquakes to subtle tremors, even deep underground rock bursts. I mean, these things are a massive, persistent global threat.
They really are. And traditionally, geology has relied on a historical data, on these really complicated physics models.
But they have their limit.
Exactly. The sheer complexity of what's happening down there,
Yeah.
it just outpaces what conventional analysis can handle. You need something that can integrate all these different characteristics, geography, timing, energy all at once.
Which is the mission for this deep dive, right?
Right.
We're unpacking research that uses deep learning to get past that siloed analysis.
That's the goal. We're looking for a shortcut to a much more precise kind of disaster analysis. Training these models to classify events by type, by location, by magnitude. It's not just about seeing what happened, but really understanding why it happened and where it fits in the global picture.
All right, let's get right into it. The source for this is a massive global catalog of seismic history. So to start, what exactly did the researchers feed into these AI models?
Well, they started with this foundational data set. It spanned 52 continuous years, from January 1st, 1965, all the way through the end of 2016. It's just an immense record.
Half a century, wow, half a century of global quakes and rumbles.
Precisely. And while it is a global data set, it's naturally biased towards the most active zones.
Like the Pacific Ring of Fire, I assume.
Of course.
Yeah.
But the crucial part is that the records were meticulously complete on the key attributes for every single event.
Yeah.
So you have date, time, latitude, longitude, depth, and magnitude. Having that comprehensive baseline is, it's the absolute first step.
Okay, let's unpack that. Those attributes are pretty standard, the what, where, when, and how powerful of an event. But where does the AI novelty really come in? I mean, we know machine learning really thrives on smart feature engineering.
Right.
So how did they turn these, simple coordinates and magnitudes into features that actually capture the dynamics of the system?
That's where this analysis just shines. They didn't just use the raw data. They created 5 really innovative features and grouped them into 2 categories to capture both the spatial and the energetic dynamics. So the first category is location-based features. The first 2 features here are the latitude and longitude ranges. And these are calculated within specific time windows.
Hold on, a range. Why look at a range instead of just a single point?
Because seismic activity isn't static. These ranges, they capture the spatial extent of events over a period of time. If you track them, you're essentially watching the perimeter of the seismic activity grow and shrink.
So it highlights shifts and hotspots.
Exactly. It's like drawing a fluctuating box around the action, not just putting a pin in a map.
Okay, that makes a lot of sense. It captures the wobble of the fault line. What was the second geographical feature?
That was the distance from the previous event. This is so key for understanding movement. It quantifies the separation between consecutive events, so the model can track how things are progressing in space.
So are the events clustered together, suggesting aftershocks, or are they migrating somewhere else entirely?
Precisely. It signals a much broader tectonic shift if they're moving.
Okay, so we have the location features. What about the ones that track the actual, the physics of the events, the power?
That brings us to our second category, seismic characteristic features. The third feature overall is magnitude variation. This is just the difference in magnitude between one event and the next.
Right, so we're looking at volatility, not just the absolute size. A jump from a 4.0 to a 7.0 is a much bigger deal than 2 5.0s in a row.
A huge signal. And this variation is incredibly useful for tracking trends. Think about a foreshock, main shock, aftershock sequence. And just as a quick reminder for everyone, magnitude is a logarithmic measure of the energy released.
And for the big ones, they use the moment magnitude scale, MU-W, right?
It's the standard, yes, for anything 5.5 or greater. Then, feature number 4 is the seismic energy estimation. This approximates the total energy released in joules.
And this is different from intensity, which is what people feel on the ground.
Very different. Intensity is about the shaking, the damage at a certain location. This is about the raw destructive potential right at the source.
Got it. And what's the final feature, the geometric one?
Yes, the horizontal to depth ratio. This gives us a geometric perspective on the event's structure. If you have a high ratio, it might signal a very shallow event with a wide impact area. A lower ratio could suggest something deeper, more focused. It's a way for the model to sort of visualize the event's shape.
So, with those 5 features mapped out, the researchers started with something simple, a rule-based analysis. What were some of the low-hanging fruit insights that this massive data set offered up right away?
Well, the initial rules confirmed some really established geological ideas with stunning confidence. Take Rule 1, magnitude and depth correlation. The rule is simple. If the magnitude is greater than or equal to 5.6, then the depth is greater than or equal to 15 kilometers.
So on average, the bigger the shake, the deeper it comes from.
That's the takeaway. And this rule was so robust, it achieved 75% accuracy and 80% coverage across the whole data set. Geologically, this is key. It really supports the theory that larger events need the immense pressures you find deep down, where tectonic stress can build up.
That's a powerful validation of basic Earth science. But I'm curious about the spatial rules. What did the algorithms tell us about where these events cluster?
The second rule, the spatial correlation, was fascinating. It pinpointed a specific, really consistent hotspot. It found that if the longitude is greater than or equal to nautical 40, then the latitude is approximately -15, and this had over 82% confidence.
82%. Wow. And for those of you without a globe handy, longitude -40 is roughly down through the Atlantic toward Brazil. Latitude -15 cuts right across South America. So this rule basically identified a massive seismic hotspot on the Atlantic side of South America.
That's right. It mathematically validates the existence of this critical, consistent zone in that region, which is, of course, vital for regional preparedness.
So those simple rules gave a great foundation. But to handle the full complexity, where the relationship between magnitude and depth isn't just a straight line, they turned to clustering.
Yes, K means clustering. It's a form of unsupervised learning, which means the AI had no preset labels. It just looked at the relationship between magnitude and depth on its own.
And what did it find?
It identified 10 distinct clusters, and each one represented a different tectonic context.
So the AI wasn't just randomly grouping data points. It was, in a way, mathematically rediscovering things geologists have known for centuries.
That's exactly the insight. The clusters automatically separated different earthquake types. For example, one cluster contained all the shallow upper crust earthquakes from 0 to 70 kilometers deep, the kind you see in Japan or Chile. Then another cluster captured those intermediate depth events, what are called Wadati-Benioff events, for 70 to 300 kilometers deep. And then a third cluster highlighted those really rare, extreme, deep focus shocks, 400 to 700 kilometers down, the kind you see near Tonga, Fiji. The AI put precise numerical boundaries on these classic tectonic zones.
It's amazing. All that complexity reduced to a handful of clusters from just 2 variables.
Okay, now we get to the heart of this deep dive, the machine learning model showdown. The researchers deployed 7 models in total. But when we talk about success, which single metric actually matters for real-world risk assessment?
That is the most important point of the whole study. You have to look past the training accuracy. That's just how well the model memorized the answers from the past. The crucial factor is testing accuracy.
Right. That determines its ability to generalize, to classify an event it has never seen before. That's what you need when the next one hits.
Makes total sense. A model that knows history but can't predict the future is, well, it's useless for preparedness. So, on that unseen data, which model came out on top?
The models separated themselves pretty clearly, starting with the winner, random forest. It achieved the highest accuracy at a really robust 78%.
Random forest. Okay, for anyone unfamiliar, that's an ensemble method. It's like having a jury of hundreds of different decision trees all vote on the right answer. So why did this more complex model outperform the simpler ones?
Because it's just incredibly robust. It excels at modeling these complex interacting variables, depth, magnitude, location, all working together. By using so many trees, it minimizes the risk of one single, slightly flawed decision path, ruining the entire classification.
But if it's that complex, doesn't that make it a bit of a black box? How do we know that 78% accuracy is based on real geological insights?
That's a great question, and it's why comparing the models is so important. We can see that the simpler models, while less accurate, still performed really well, which suggests the core insights are sound. The standard decision tree model, for example, hit 75% accuracy on the testing data.
Only 3 points lower.
Right, and below that, the support vector machine, or SVM, was remarkably consistent. It held steady at 72% accuracy on the test data, no matter how they tweaked its parameters. That kind of consistency tells you the features they engineered are doing their job.
So the data is structured cleanly enough for multiple models to get a good read on it.
Exactly. Moving down the list, K-nearest neighbors, or KNN, achieved 70% accuracy, still very effective, and bringing up the rear was logistic regression, which had the lowest accuracy at about 68%.
So the big takeaway is pretty clear. While the simple algorithms confirmed what we already knew, the more advanced random forest model proved to be the most robust classifier when faced with new, unseen data.
Yes, it really cements the value of this kind of machine learning in interpreting the Earth's processes. And, the significance of getting a 78% accuracy here extend into some really critical real-world safety applications.
Okay, so what are some of the most relevant applications for you, the listener, right now?
One of the biggest is being able to distinguish between natural seismicity and induced seismicity. Those are events caused by human activity, things like hydraulic fracturing or depleting reservoirs in oil and gas exploration.
So these AI models can actually tell the difference between a natural tremor and an industry-caused one.
Absolutely. Because the models classify events based on their precise depth, magnitude variation, and location, they can quickly spot the unique signature of an induced event, which is often much shallower and located in very specific non-tectonic regions. This is immediately useful for regulators and for energy companies. And beyond that, the analysis helps a lot with understanding tectonic processes and critically classifying aftershocks quickly after a major event. That's essential for ongoing risk assessment and emergency response.
And it filters out seismic noise too, right?
It does. It enhances the sensitivity of our monitoring systems and even helps with broader environmental monitoring, like detecting deep landslides and rockfalls.
So what we've seen today is really the power of AI to synthesize half a century of global data, moving us closer to proactive defenses against these unpredictable events. The work shows that AI is just a phenomenal interpreter of geological history. But here's the final provocative thought I want to leave you with. The research noted that several secondary data attributes, things like statistical depth error or magnitude error, were often missing from the global catalog. They just weren't reported consistently. So if these models are already hitting 78% accuracy with partial data, what kind of breakthrough could AI achieve if those crucial, nuanced parameters were collected globally? Could we push past 90%? That gap between what we could know and what we actually do collect, that might be the next major fault line in disaster mitigation.
That's a profoundly important question. Closing that data gap really is the inevitable next step in this science.
Thank you so much for joining us on this deep dive, and thank you for taking us through this incredibly detailed work.
It was a pleasure. Goodbye.